Hi guys. Hello. So we are here to go over the stopping distance lab summary. So we are on page 23 of the packet, I believe. I think it's 24. 23 and 24, yeah. So we're going through, starting with the analysis question. So hopefully you got some pretty good data yesterday, but you should have found that the stopping distance is proportional to velocity squared. So your proportionality statement would be that distance is proportional to the square of the velocity. If you didn't get that data, it's not the end of the world, but that's really what we would want you to find. So we want to prove that using energy. Like, where does that come from? So starting with our base equation, energy initial plus work equals energy final. That's what we always want to go to. And this comes from our LOL diagram. So initially, the Jenga block was moving, so it had kinetic energy. And then friction, which is not part of the system, the surface was not in the system, so that was work done by friction. It was negative, it was taking energy out of the system. And at the end, the Jenga block wasn't moving, so it had zero kinetic energy. So this is our energy conservation equation. So we go ahead and we solve that. Before we do that, we want to know why is work negative. So how do we know for certain using math that that's negative? Well, on Wednesday we found the equation work is equal to force times distance times the cosine of theta. That theta is the angle between the force and the distance. And so it's not necessarily the force's angle, but it's between force and distance. So we have our Jenga block sliding to the right in this case. So friction's acting to the left, but it's moving to the right. So the distance is to the right. The angle between those is 180 degrees. They're going in complete opposite directions. And so if we plug in 180 degrees here for the cosine of theta, that's a -1. So that's where that negative here comes in for work, to make the work negative.
Okay, so now we're going to kind of go through our nice little equation. As always, we do a lab and sometimes we can derive some more simple equation or an equation that tells us more about the situation. So we had k is equal to a negative WFK equals 0. So I can plug in what I know already. We know that kinetic energy, we can relate that equation as 1/2 mv squared. And then we can write the work done by the force of friction as Fk d, that's our work, it's force times distance, and then the cosine of 180, because like Rona said, they're going in opposite directions. Next, we can simplify even more. We know that the force of friction can be written as mu times Fn, and you'll notice we kind of simplified already. We know that Fn is also equal to Fg, so we have mu times mg times the distance. This section alone right here is W, force times distance, and then we take into account the -1 as seen as we're going in opposite directions. One thing to note is to make sure that you don't add a negative twice. So you have a -1 here, which represents that negative work done by the force of friction, but we don't want it to be kinetic minus the negative work done by the force of friction, because that would be a double negative and that would end up not having a final energy of 0. So make sure that you're placing your negative somewhere and you're not doing it twice. We can simplify once more. We can cancel out our masses here, and we have 1/2 v squared is equal to mu times g times distance. And notice we've factored that -1 in, so it's now a minus. Then we simplify even more. 1/2 v squared is equal to mu times g times distance, and we can finally say we know these relationship. We also have d and v squared on opposite sides of the equal, which further proves that these two are proportional to one another. And then we're going to move on. I think that's it.
So looking at page 24, it asks you to show how you can use your slope to find Fk. So it wants you to do this symbolically. So let's go back to our base equation, which was kinetic energy minus work due to friction is equal to 0 energy at the end. I'm going back to this because we need force of friction in there. If I'm trying to find it, we can't use that final factored out version, the really expanded one, because there was no Fk. It was just mu and gravity and distance. So let's go back to this, and we're going to expand only to the point where we still have friction in the equation. So we have 1/2 mv squared is your kinetic energy. work due to friction is force, so Fk, times distance, times cosine of theta, which is 180 degrees. If we put that 100 cosine of 180 as a -1 and put it in front, that turns into a minus sign. So we have 1/2 mv squared minus Fk times the distance is equal to 0. You're starting to see how I can use the slope to find Fk. So moving that to the other side, you get 1/2 mv squared equals Fk times the distance. Your slope, if you remember, our rise was distance and our run was velocity squared. So we want to get distance divided by velocity squared on one side of the equal sign. So I'm going to divide the velocity squared over to the other side and divide the Fk to the other. So what you're left with is the 1/2 m on one side and the Fk in the denominator is equal to the distance divided by the velocity squared. So this would be your slope, whatever slope you got. Let's say you got a slope of 10, it equals m divided by 2Fk. So in order to solve number 4, all you would need to do is rearrange this equation to solve for that Fk. So the rest of these are mostly proportional reasoning questions. So we're going to post the key. So we just want you to go to Haiku, make sure you check all your answers, and come with questions Monday. We will answer questions and whiteboard worksheet 4 before the quiz.
All right, that's it. Good
We
luck,
miss you guys.
Bye.